Video 5 is all about electromagnetic induction. And this starts out with Michael Faraday, who did an experiment involving an iron ring and two coils of insulated wire. Okay, and he was known, and this setup was known as a transformer. So he looked at a transformer, essentially, and how a current was induced in a wire that was not connected to a power supply. So what he did was he had this iron core. Right, here's my iron core. And this had two coils wrapped around it. So I'm going to wrap a coil on one side that's connected to a battery. So let's put a battery out here. Right, and we'll wrap this around and go behind and then in front and behind, in front, behind, and in front, and then it will come out. So this is connected to a battery. On the other side, he had another coil that was connected to a galvanometer. Now, if we were in the classroom, I could show you this. This looks just like any of the other devices we would be using, like an ammeter or a voltmeter, but it's not powered by anything. It does have a positive and negative side, and typically it has a dial, right, like a little screen here with a needle that's going to deflect. And so this again was connected to a coil of wire, something like that. Right? And so one thing to remember is that this is a power source, right? Let's give this positive and negative side. When the battery was turned on, current was running through this wire, right? And so you have this flow of electrons. As the current is traveling through this wire, the magnetic field in the wire is getting stronger, right? Around the wire, is getting stronger. And so when you have this wrapped around iron, it's going to start to build a magnetic field in the iron itself. Right? It's hard to draw, but in the video they show you that building of the strength of this magnetic field in the core, the iron itself. And as the current starts to travel through this and the magnetic field grows around the wire, there's a changing magnetic field in the iron. So the galvanometer deflected in one direction, right? So it deflected and then it went back. And then when you stop the current, right, the magnetic field is now going to disappear. And again, you have this changing field in the core. So again, if you haven't watched video 5, I definitely go back. They show you exactly how that is occurring. Right? It's not very easy to draw, but the animations in that video are really great. So when the field collapses, again, you get this deflection in the other direction, right, just for a moment. Right? And that deflection here, this galvanometer, measures current. And so when that deflected, that means that there was a current running through this wire, even though the wire is not connected to a power source. Okay? So one thing to know about a transformer and what Faraday did was he determined that a changing current in the primary coil, right? And so you have that primary coil that's connected to the battery, right? This is your primary coil over on this side. When you have a changing current, so you turn the battery on, the current builds, it's inducing, so changing current in the primary coil induces a current in the secondary coil. Okay, and the key here is that this is changing. So when the current builds and it gets as strong as it's going to get based on that battery, then the primary coil has a uniform magnetic field around it, which means that you will not have a changing field in the iron core, so the galvanometer will go back to reading 0. When your magnetic field is apparent, it's there, but it's not changing, then there will be no current induced in that secondary coil. Okay? So the key here is that as long as the magnetic field is changing, I'm going to abbreviate magnetic field, as long as the magnetic field is changing, and that could be growing or disappearing, a current will be induced. Okay, and then in regards to this setup, this transformer setup that Faraday had, as long as the magnetic field is changing in the iron core, right, that's where this is occurring. A current will be induced essentially in the secondary coil. Okay, and so that's essentially how transformers work. And the other thing that video 5 talks about is Lenz's law. And this is something really important. There's a really neat demo that we could be doing if we were in the classroom with a copper tube and two pieces of metal. One of them is a magnet, right? Here's Lenz's law. So you may want to pause this, definitely get this definition down. An electric current induced by a changing magnetic field, that goes back to that transformer, will flow such that it creates its own magnetic field that opposes the field that created it. Okay, so again, we have this changing magnetic field, right? And you're inducing a current that flows so that it opposes the field that created it to begin with. So again, in the video, they show you some really great animations. I am going to draw a few different things here. So let's say we have a coil of wire. Right? It's connected to a power supply. You could have it connected to whatever you want. And I'm going to bring, actually it doesn't even have to be connected to anything. It could just be a solenoid, right? Connected to nothing. I'm going to bring a bar magnet into the center of this. Right? So let's say this is the North Pole and this is the South Pole. And I'm going to move the magnet to the left. So the North Pole going into the coil itself. Right? So if you imagine, right, we're going to bring this bar magnet into the center of that. And there'll be a current that gets induced in this coil that's going to oppose the motion of this. So I have a North Pole moving to the left. And to oppose that, you're going to have something that's pushing it back out towards the right. And what pole would push or oppose a North Pole? What is going to essentially kind of push this back away from itself is another north. So when I bring this bar magnet in here, I'm going to create a North Pole on this side of the magnet, or excuse me, the coil, and a South Pole on the other side. And that indicates to you the direction that the current will flow. Right? And so if you use left-hand rule number 2 for coils, right, fingers go in the direction of the current and my thumb shows me where the North Pole is. So that means that current is going to go up around front first and then behind. Now if I do the same thing, so now let's pretend that that magnet is in the coil already. So I'm just going to draw my coil again. But now this bar magnet is, let's say, like halfway in. Right, so here's the North Pole. And now I'm going to pull this out. Right, so that's the motion of this. I'm going to pull it out of the coil. And the coil is going to create, right, a magnetic field. So we have a changing magnetic field because the field is coming out of that coil. The current in the wire will flow such that the field opposes the field that created it. So pulling this out, right, we have a North Pole coming out, and the coil is going to create a field that tries to keep the North Pole in, so it's going to pull it back to the left. And what's going to pull a North Pole close to it is a South Pole. So that means when I take this bar magnet and pull it out of this, the coil is going to create a South Pole over here to try to keep the magnet close to it, which means that the North Pole gets created over here. So if that's the case, and I use left-hand rule number 2 again, you can see my thumb has to go this way. So current is now flowing in the opposite direction, right? So it's coming up from the back and around. Right? And so that's what this is all about. You will see some questions like this on your quiz later this week. So you definitely want to make sure that you know that this is your key, right? This opposition, the field that gets created opposes the motion. So if you're bringing a pole into the coil, essentially you're going to create the same pole there to try to push it away. If you're pulling the magnet out of the coil, you're going to create the opposite poles there to try and keep them together. here's another look at electromagnetic induction. This is one of the PhET simulations. You'll notice here we have a coil of wire that's connected to a light bulb, and then around that light bulb we have a voltmeter. One thing you should notice is there's no power source here, but we can use electromagnetic induction to light the light bulb. Right, so over here you have a bar magnet, and I am able to move the bar magnet around. And so if I take this bar magnet and I move it, I have a changing magnetic field. So as I move it closer to the coil, the magnetic field inside the coil is going to get stronger. So as I bring that into the coil, you can see that the bulb lit for a split second. And if you looked carefully, the voltmeter read a negative voltage, right? So it just deflected to the negative side. You'll notice the bar magnet's still in the coil, but nothing's happening. There's no light from the light bulb. There's no voltage on that voltmeter because the field has stopped changing. Now again, if I take the magnet out, right, we get light again as the magnetic field is changing, and you'll notice the needle on the voltmeter deflected in the opposite direction. This goes into Lenz's law, where the field that gets created in the coil is going to oppose the field that's creating it from the bar magnet. So as I bring this into the coil is going to generate a magnetic field that opposes a north pole coming in, right? So it's going to create a north pole over here to kind of try and push the bar magnet away, opposition. So as I do that, you see that the voltage deflects to the negative side. Right now, when I go to pull the bar magnet out, again, I have a changing magnetic field, and the coil is going to generate a magnetic field that opposes that motion. So that means that it's going to create a south pole over on this side of the coil to try and keep the bar magnet in, right? It's going to try to attract it. So as I pull it out, you can see that again, my voltage deflects the other way, right? So as it goes in versus out, and it's only when the field is changing that you get that deflection. Now watch what happens when I drag it all the way through. So remember, the coil is always going to create a field that opposes it. So as I go in, and then I drag it all the way out, right? So a similar thing is happening. The voltage goes negative, then positive. So I'm going to do that again. I'm bringing it around. So on the way in, it creates a north pole on the right-hand side of the coil. As I go out, it creates a north pole on the left-hand side of the coil, which is going to cause the current to travel in opposite direction, which is why you get that opposite reading on the voltmeter.